Thank you. I'm Flora Salim. I'm a professor at UNSW, Sydney, and this is actually a paper of my student Peibo, who is co-supervised by Maarten from University of Amsterdam and myself. So Peibo is based in Sydney, but he didn't manage to come here because of visa. So that's why I'm here. And just like Peibo, it's actually my first SIGIR, so I'm actually more on machine learning data mining community. And this paper, basically, I don't think I have to convince you that POI data is actually quite important, especially in urban planning and providing useful information for travelers, visitors like us. I mean, how many of you here are visiting DC for the first time? Okay, me too, right? So, and you're on your map trying to navigate and search for information. And actually, for example, a company like Yahoo Japan use POI data to understand visiting patterns and also then provide recommendation on good time to visit, for example. And so for those of you who are not familiar what POI data and LBSN data contains, it typically contains static information, such as location information, and then semantic information, which includes the type of POIs, the descriptions associated with it, and also historical information such as customer check-ins. Now, the question that we have is, a lot of this information, there's a lot of auxiliary information, additional information that we can potentially ask LLM or utilize LLM directly in modeling. So the question is, then can we utilize the rich semantic knowledge of POI from LLM for more accurate next POI recommendation? Now, but to be able to answer that, we actually, to test the intuition first, we look at, if can existing pre-trained LLM be used to analyze LBSN data. So what we did was first, let's see if we can just load any check-in data sets like Foursquare or Goala data set that some people here have mentioned before in their previous talk. So we did try that. So I got my student to do that, and so Peibo actually loaded one of the training data set, a sample data set, and asked ChatGPT to actually summarize it. So describe the characteristic of the data. So that was the first part, and the second part we prompt ChatGPT to find unique POI category names. So it managed to do that. And what we asked is the next thing is summarization tasks. So we asked ChatGPT to summarize if you can actually find category names that have intersections with the context. So the result is this. So you didn't manage, if you read the paper, you won't be able to get the details of this, but there was a process to get to this table. That's basically the POI categories of the data set as summarized by ChatGPT. So ChatGPT came up with this category, which is pretty cool. We didn't actually tell them, right? Here are the categories of Foursquare, but just based on the data set, historical data set itself that has the subcategory, it managed to do summarization pretty well. Okay, so we established the fact that LLM does have prior knowledge about POI semantics, okay? So we're thinking about, okay, let's do a bit like experiment. Can we do zero-shot prompting? And it is actually, in fact, very difficult. So there's still a bit of challenge to basically just parse every single historical information to an LLM. First, of course, historical data of check-ins can be very long, so there's a limitation to that. I'll talk more about the challenges, but why LLM, the motivation here really is, can you then parse a lot of contextual information and historical information right away per every user directly to LLM and ask LLM to come up with a response of where the user will likely go next, or even can you recommend POIs that the users will go next, okay? So LLM has rich contextual understanding, and then also integrate different data types, because you can see the data types here. It even has date, it has location of information, it has the category information, because you can actually parse them all as natural language. Now, sample check-in data as on Manhattan here, as you can see, there's a series of movement, and often even state-of-the-art paper like SCSGCN from SIGIR 2023 used for this POI prediction task, it actually failed to predict exactly the next location these particular users will go next. So the reason for that is actually traditionally a lot of the work on this domain is is what we call feature transformation paradigm. So what you have is raw data with of check-ins, right? So a lot of raw, and then you need to add embeddings. You have to add semantic information about that historical data. So what is that POID, entails, and who else have been visiting that POIs, and whether there are those who are actually closely related to who actually have checked in. And you learn these embeddings together in encoder-decoder architecture. And we've seen this as well in a lot of, there's so many papers in the last few years on this kind of paradigm. Okay, so what is actually, there's a major issue with this. So semantic knowledge of contextual information has to be encoded manually or basically learned. And you can see in the feature transformation paradigm, these two are the papers from SIGIR 2023 and 2022. Like, you can consider them as recent state of the art in this domain, but you can see in this method, they're actually very complicated. The architecture is just getting more and more complex because it's basically, bottom line often is a transformer architecture with a lot of individual layers, additional layers, and embeddings, right? Now, in this paper, we propose a completely new paradigm, which is a language paradigm. So what it means is, can we actually directly do contextual prompting? But the question then, how do you do this prompting? And then pass the prompt into LLM to get a response. Now, so 3 parts to this challenge. First, how to transform the task into a question answering task rather than next location prediction, which is more sequence to sequence prediction. Second, how to fit that historical data that has a lot of varying lengths for different users into a limited context window. And the third is how to then align the LLM with the application or the response. So we present LLM for POI, and the contributions are 3 parts. First, it is the very first framework that you utilize LLM for next POI recommendation task. And second, we come up with a prompt-based trajectory similarity to combine information from historical trajectories across different uses. I'll show you how we did that, and we are also the first to fine-tune LLM on standard size LBSN datasets, so we can then exploit the common sense knowledge from the LLM. So that's basically the figure of the off-roll method. So 3 parts to the method is the key query similarity to be able to find the right historical data that is actually useful to be parsed into the prompt. And then trajectory prompting, there are 4 blocks of the trajectory prompting. And then we did supervised fine-tuning. So let me go and explain that one by one. But to make it easier, I'll start with number 2. So this is the structure of the trajectory prompting. So the prompt consists of this question block, okay? The following is a trajectory of user and given the user ID, okay? And this is the check-in records of that particular user ID. So at time, certain time user visited POI and the ID with category ID. And there's also historical data, which is this is the historical trajectory block, the purple block. That also then we parse this check-in record at this format. And then the instruction block is in the orange color. So if you look at the instruction block, given the data at certain time, which POID will user ID visit. So this is in future, okay? It's not something inside the question or the historical. Note that POID is an integer from range of 0 to, we give the range based on what is known of how many POIs there are in that particular city. And the answer, and then the answer block, which is at time, user ID will visit POI. So the, LLM, you need to predict the the POI ID. So the method first one is the key query similarity, because as I said, this historical record can be very long, but we have very limited context window. So what we did then, The key prompt is basically the question, and we come up with the query prompt pairs, which are basically consists of all the historical data that could be potentially candidates as a pair of this key prompt. And we actually compute, for each of the key prompt, we compute the similarity between it and all the query prompt before it. And for each pair of the key and query, we feed them into a pre-trained llama. So this is a llama that's not fine-tuned, so this is a zero-shot prompting. And then we compute the cosine similarity using the features from the last hidden layer. So finally, then we can form the prompt, and the historical trajectory with it has the highest similarity are actually then used. So I've shown you already that how we did the trajectory prompting and how we performed the key query similarity. So once we've done that, the next part is we did supervised fine-tuning. So we have a training data set where the input is loaded. The pre-trained LLM is loaded with quantization and flash attention. And then with the answer part is used for to guide the fine-tuning with Flora. So at the end, we actually have a fine-tuned llama, okay? So if you remember, I mentioned we computed key query similarity here. This is a different llama. This is the pre-trained one, whereas in here, we come up with a fine-tuned LLM based on the LBSN check-in data sets. So the data sets are consisting of Foursquare, New York City, Tokyo, Gowalla, and here are the main results. So I mentioned a couple of state-of-the-art methods, including those from SIGIR, some from KDD and HKI. And if you can see, most of these ones are actually graph-based methods, and we have three different combinations of the fine-tuned models, either fine-tuned including all history or other users. So this is the one without, and just with history and with other users. So the reason for that is because some of the, for fair comparison, some other models did not include history or some did not include other users. So if you, for example, want to compare the performance of LLM POI with Stan, you should use the first star. Whereas the last two are, it's best to compare with LM4 POI. And you can see the performance improvement is quite significant. So if you look at these ones, right, they are quite marginal, but you can see here it's quite a big jump in performance. So further analysis on cold start. We look at, we rank the users based how active they are, how many check-ins they have. And the top 30% we consider very active, and the bottom 30% are inactive, and in between is normal. And state-of-the-art, cold start didn't work that well. Ours work very well. The same thing here. And even it's better on normal. But on very active, you can see actually is very much similar or even sometimes worse. So that means, because I think in here, if you remember, in our LLM for POI, we didn't parse all the historical trajectory, okay? Whereas in this other method, they use all the historical trajectory, okay? So that's the main difference. So that's why we're losing, because we didn't actually use all historical information. But you can see that in general, so the top 70%, even the inactive one, we are a lot better. In terms of trajectory length, some users have very short trajectories, some actually have long, so it depends on how active they are. You can see that our methods work really well even on short trajectory types, whereas a lot of other methods, graph-based ones and transformer-based ones, are very much dependent on long trajectory or long history. What is even more interesting is if you've trained the, so this is the scaling laws at work here. So the data is trained on NYC, tested on NYC, and another one, you can look at this comparison. Trained on Tokyo, but tested on NYC. But the model trained in Tokyo is actually better than the model trained on NYC, tested on NYC. Okay, so when we look at this is actually interesting. But one of the key reasons that we think why Tokyo model works a lot better across is because there's so many check-ins in Tokyo, like I think almost 3 times. So I think that tells you even information from another city can be used, and it has this good transfer capability. But again, more training data is useful for LLM-based method. Yeah, again, for the ablation, I don't think I have time to talk about this. So in conclusion, we propose the very first framework to deploy LLM for an XPOI recommendation task. And we propose this trajectory prompting and how you came up with the right prompt to transform the task into QA task. And to alleviate the close-out problem, we can introduce the key query similarity method. So there are a couple of limitations. Fine-tuning runtime is a bit slow. The design of prompts is limited by context length. There are actually more recent work right now with how we can actually address these things. So, and currently we also only focus on delivering a single correct answer, so top 1. So I think we should extend our methods to scenarios beyond just recommending single best item. So that's it. That's the paper. A quick pitch. I'm hiring. So if anyone in this interested, reach out. A couple of postdoc and PhD positions. So thank you so much. If you like to know more about the paper, you can check it, or you can scan the QR code for the code. Thank you.
Thank you very much.